There are some acids that have 2 protons and they can donate 2 protons. And usually what happens is they'll donate 1 proton and then the second one. So they don't donate them both at the same time. And then some acids have 3 protons and they can donate all 3 of them, but 1 at a time. If an acid only has 1 proton to donate, it's called monoprotic. If it's got 2 protons to donate, it's diprotic. And if it's got 3 protons to donate, it's called triprotic. Usually, once you're more than 1 proton, they sometimes call them polyprotic acids, meaning they have more than 1 proton. So an example of a monoprotic acid is HCl. An example of a diprotic acid is H2SO4. And an example of a triprotic acid is H3PO4. We're going to learn the names of these acids in a little bit. This one over here is interesting. Can you see that you've got a total of 4 hydrogens in this? But notice that you have 1 hydrogen up front and then 3 in the middle here. This happens to be an organic acid. It's acetic acid. And only 1 of the 4 hydrogens is an acidic hydrogen. So they put the 1 acidic hydrogen right in the front. And these ones are in the middle. These are non-acidic hydrogens. Non-acidic hydrogens. And if any of you guys are planning on taking organic chemistry, if you take a look at the structure, the Lewis structure of acetic acid, it's got 2 carbons, it's got a total of 4 hydrogens, and it's got 2 oxygens. And this is what the molecular formula says. But the Lewis structure shows you the difference between this acidic hydrogen and these 3 non-acidic ones. This acidic one is attached to an oxygen. This is the one that can be donated. These 3 are attached to carbons. They can't be donated. Since you haven't had organic, you're not going to worry about this right now. Always just look at the hydrogen right in the front. That will tell you how many of the hydrogens are acidic. And then all the other hydrogens in the middle of the molecule, those are considered non-acidic. All right, so I wanted to show you how a triprotic acid, for example, this phosphoric acid, can donate its protons. So it's a stepwise process. So H3PO4, let's say it's going to donate its proton to water. So this is a weak acid, and we're going to learn all the weak and strong acids in a little bit. But phosphoric acid donates 1 proton to water. Water becomes the hydronium ion. And then what's left over? H2PO4 minus 1. Remember, the conjugate base always has 1 more negative than the original acid. Okay? And 1 less hydrogen. So now I'm going to take this guy, bring it over here, H2PO4 minus, and get another molecule of water and do a stepwise process. So the first proton was donated to water. Now the second proton is going to get donated to water. So this gets donated to water, becomes H3O plus, and then what's left over? This conjugate base is going to have 1 less hydrogen and 1 more negative. So you're going to have HPO4 2 minus. Okay, now we take this, bring it over here. HPO4 2 minus, a third molecule of water. What's going to happen? Now this H is going to be donated to water, H3O plus, and then your conjugate base is going to have 1 less hydrogen, and you end up with the phosphate polyatomic ion. So this is the stepwise process. When you have a triprotic acid, it's 1 step, 2nd step, 3rd step. If it was diprotic, it would be 2 steps. Okay? All right. Now, there are a whole bunch of acids out there. I want you guys to know the 7 strong acids. In your book, Stoker says that there are 7 strong acids. What do I mean by strong? That means they donate a hydrogen ion completely. Basically 100% donation, 100% dissociation. It goes, basically the equilibrium is far to the right, okay? It's not coming back. So what are the 7 strong acids? Well, you know the halogens. Skip fluorine because hydrofluoric acid is not strong, but hydrochloric acid, hydrobromic acid, hydroiodic acid. So this is called hydrochloric. This is hydrobromic. And this is hydroiodic acid. Acid. Okay? We need 4 more. There's this guy, H2SO4, is sulfuric acid. Sulfuric acid. HNO3, you recognize the polyatomic ions. The sulfate polyatomic ion is -2, that's why you have 2 hydrogens here. Nitrate polyatomic ion is -1, that's why you have 1 hydrogen. This is nitric acid. And then HClO4, recognize the perchlorate polyatomic ion with -1, and this is perchloric acid. And then HClO3, this is chloric acid, because you recognize the chlorate polyatomic ion. Okay, these are the 7 strong acids. All other acids are considered weak. That means they do not donate that 1 proton completely. They do not completely dissociate into a hydrogen ion and whatever other anion is left. Okay? If you memorize the 7 strong acids, or just have them in your head, those are the 7, any other acid you come across will immediately be weak. Well, how do they rank the weak ones? How do you know which one is the strongest of all the weak ones? Well, the way you do that is you use something called an acid dissociation constant, or Ka. Remember K equilibrium? Remember that from the last chapter? Now we're just going to call it Ka. Hold on 1 second here. Let me see where the chapter, the book, if they have. Yeah, they have a table 10.3. Table 10.3, if you want to take a look at the book, it has the acid ionization constants. The bigger the Ka, the stronger the acid. So they don't do Ka values for strong acids, because remember, in order to do any equilibrium constant, you're putting the products over the reactants, the concentration of the products over the reactants. Well, when something is a strong acid, remember the equilibrium is far to the right, so the number is like crazy high, big, infinity. So there's really no point. And there's very little on the left side. So if you're going to divide by 0, you end up getting infinity anyway. So no point. But there are Ka values for weak acids. So you always get Ka values for weak acids. The bigger the Ka, the stronger the weak acid. And if you look at that table, this is table 10.3, it gives you a bunch of numbers. Let me take a look real quick here. We have phosphoric acid has a Ka of 7.5 times 10 to the -3. So 7.5 times 10 to the -3. This is phosphoric acid. All right. For another acid, carbonic acid, H2SO3, it's 4.3 times 10 to the -7. 4.3 times 10 to the -7. And this is carbonic acid. This one is phosphoric acid, and this is carbonic acid. You can see that neither one of them is one of the 7 strong ones. So these are 2 weak acids. So if you're comparing the 2 weak acids and someone asks you which one is stronger of the 2 weak acids, you can see here from the Ka value, the acid dissociation or ionization constant, This is a bigger number than this. This is 10 to the minus 3. You move the decimal 3 places. This one, you move the decimal 7 places. So this is a much bigger number than this. So phosphoric acid is a stronger acid. It dissociates more than carbonic acid. Okay, that's the way you read Ka values. All right. Before I wrap up this video, let me give you the strong bases. So you have 7 strong acids. Which ones are considered the strong bases? The ones that completely dissociate and produce a very basic environment. Group 1A, metal hydroxides. So any metal in group 1A, lithium, sodium, potassium, rubidium, all of those with a hydroxide, that's considered a strong base. So lithium hydroxide, sodium hydroxide, potassium hydroxide, etc., etc. All group 1A. Also, heavy group 2A hydroxides. So looking at the periodic table, heavier, calcium, and heavier. So calcium hydroxide, barium hydroxide, strontium hydroxide, okay? Not magnesium hydroxide, that's not heavy enough. So these guys and these guys, those are the strong bases. Okay.